So today, this talk, as Alex introduced, I'm going to talk about my recent work on how to secure the internet without overhauling it. So please feel free to interrupt me and ask questions. I like interactive talks. All right. So as we all know that the internet was designed in the old times, so that it's vulnerable to many attacks. Like for instance, the IP prefix hijacking attacks, where a rogue network may announce another network's address prefixes, say YouTube's prefix. As a result, traffic sent to YouTube may be sent to this rogue network instead. And also in the internet routing system, the malicious networks can also fake their AS paths as a result to attract the traffic that should not be sent to them. Similarly, on the forwarding plane, the internet is also vulnerable to many attacks, such as the denial of service attacks, where an attacker can control many compressed machines and send thus flooding traffic to overwhelm the network, and legitimate traffic cannot go through, and the legitimate communication will be disrupted. And even worse, to launch those denial of service attacks, attackers can spoof their packet source addresses to evade attack detection system so that they cannot be punished. So this graph shows some recent survey results done by a secure firm, Arbor Networks, among more than 100 network operators. So I think I'm being cutting off a little bit. So does anyone know how to fix this problem? So their result shows that denial service attack is one of the is the largest anticipated threat in the next 12 months, and the attack strength and sophistication just keep increasing. And the largest one in last year has reached 49 gigabit per second, which is sufficient to overwhelm most of the links on the internet. Yeah. It's okay. Yeah, I think I'm recognizable still. All right. So because this problem is so important, the National Academy of Engineering has listed it as one of the grand challenges for engineering. So this is like secure cyberspace is actually the top challenge for computer science. So in the past several years, one of my main research focus is to study this question: can we secure the internet basically with a few adoptable changes, a dirty-slate approach, instead of replacing it with a brand new internet? So by adoptable, we mean two things. First, we want the changes we introduce to be gradually deployable on the existing internet base. Second, we also want the changes we introduce actually provide immediate security benefits to early adopters, so that we can incentivize deployment. So today, I'm going to talk about our work, the conclusions we derived from this several years of study. So our observation is that many of the internet security vulnerabilities is caused by the lack of accountability in the internet. So here, by accountability, I do not mean attribution. Basically, I mean a very loose term of accountability, like holding someone responsible for its traffic. So at the network layer, the internet uses two types of identifiers, basically IP address or IP address prefix, to identify a network attachment point or a group of network attachment point. And also it uses an AS number to identify a group of routers that belong to the same organization. But unfortunately, both identifiers are spoofable, so that we cannot use them to identify bad guys, not to mention deter them. The bad traffic may evade network filters, for instance. So our solution to address this problem is this IP-made accountable architecture. So basically, for this architecture, we start from the very basic to bootstrap accountability with secure and verifiable network identifiers. On top of it, we are able to build a number of security modules that collectively make both the internet's routing plane and the forwarding plane accountable. And all those security modules are basically described by several of my papers published in the past. And today, I'm only going to have time to talk about some our latest work, basically about bootstrapping accountability, which is still under submission. So our goal is that we want to secure the internet with only lightweight and adoptable changes. By adoptable, we mean gradually deployable and incentivize early deployments. So our main approach is that we basically build using the existing infrastructure, but use them in normal ways, basically extend them beyond their current usage. In particular, we use this infrastructure secure DNSSEC to certify IP prefix ownerships. And we use inbound certificate distribution in the internet routing system itself, BGP, to make those IP prefix ownership verifiable to routers. And we also introduced some changes in the internet's forwarding plane, but all those changes are deployed using a shame layer so that they can bypass legacy routers. So now let's look at more detail of this design. So in the first part of the bootstrapping layer, our goal is to make secure and unspoofable identifiers. Here we take a hybrid approach where we use external trust to certify IP prefix ownerships. So as that is right, when the internet assigned number authority IANA allocates address to say an internet registry agent, it will create a secure binding between this IP prefix and the key of agent. And similarly, when this prefix is allocated to AS, a secure binding is created between this prefix and the AS key. Yeah, our examples are explained using IPv4 addresses, but they are applicable to IPv6 address allocation. However, we use a self-certifying approach, as in the recent work AIP, for AS numbers. So basically, we use the hash of AS key as the AS identifier in the routing system. So this hybrid approach brings a number of advantages. So first of all, it's backward compatible. We do not need renumbering renumbering every internet host of routers, and it retains the nice properties of IP-based routing. It's scalable and allows flexible prefix aggregation and traffic engineering. Also, it's also very importantly, the existing chain of trust in the address allocation process already exists. Although the internet may sound very broken, but if IANA says, okay, I allocated this prefix to agent, the world will believe it. So this is the advantages, but we also face a significant challenge. So in the previous proposals, such as the SBGP, that proposed the external trust, it faces this deployment hurdle. That is, it requires these top internet registries to deploy a PKI. But this is not a trivial task. So to address this issue, we propose, why don't we just use the top-level DNSSEC architecture as a simple PKI? So DNSSEC is a infrastructure being rapidly deployed. The original goal of DNSSEC is to ensure the integrity of DNS replies. It has this functionality allowing a parent node to delegate a DNS zone to a child. So using this feature, we propose that when internet registry allocates the address to another lower layer internet registry or to AS, it will create a reverse DNSSEC record and bind this record to the particular address owner's key. So this conceptual chain of trust in the address allocation process will be mapped into the DNS zone delegation process. Like in this example, we have this 165/8 address. Its reverse DNS record will be 165 in address.upper, and it is bound to the key of agent. And when agent allocated to AT&T, it binds the sub-prefix to AT&T's key. So this gives us this advantage. We do not need an additional PKI to create this secure prefix to key binding. So using DNSSEC has a number of advantages. So first of all, it's feasible. We could create a one-to-one mapping from an IP prefix to a reverse DNSSEC record because they share the same root of trust. Both IP address allocation and DNSSEC have the same root of trust. And also, we can create this binding by using some extended encoding rules. So note that not every IP prefix allocation falls into the class 4 boundary. There, we need to add a slash of the prefix length to using a DNS name to encode the IP prefix. So another advantages is that DNSSEC is largely available at the top level. So back in July, the top DNS zone and .upper have already been signed. And among these 3 largest internet registries like ARIN, REP, and APIC, they already signed the reverse zones allocated to them using their local trust anchors. And all 3 have stated, okay, we are going to sign the further allocations. So currently, by the time I gave this talk, so only missing link is this in address.upper. But according to ICANN, it's public email exchange, they are working on signing this zone. Once this is signed, we have the top level DNS reverse zone is completely signed. So another nice feature about DNSSEC is that it has the desirable functions we need to support PKI. It supports online queries. And use this online query feature, we actually are able to build mechanisms such as key rollover and certificate revocations. So that's why we choose to use DNSSEC to certify IP prefix ownerships. So here I show a simple example of what an IP prefix certificate looks like in our design. So basically, it has 3 key DNSSEC records. One is the DNS key resource record. Shows the address owner's key, and the other shows the hash of the key, and the R6 signature is the parent's signature, signed by the address prefix owner's parent using their private key offline. Totally, this signature field includes both inception and expiration times, just shows when this allocation is valid, and this totally is about 700 bytes if we're assuming 2048-bit RSA. All right, so for address prefix, once it's allocated to an AS, the AS may allocate it to its customers. We call it address sub-delegation. So in our design, we make this sub-delegation infrastructure flexible. An AS can choose either to use DNSSEC, or it can create a certificate server to authenticate to certify this sub-allocation. And we believe that the AS would have incentives to do so because it wants to protect its customers from address prefix hijacking attacks. All right, so now let's look at the second part of the bootstrapping problem. So having certified IP prefix doesn't solve the problem that how routers validate those prefix ownerships. To do so, the routers need to obtain those prefix. So this kind of create a problem because to obtain those prefix, routers need to contact the DNS. But before they can obtain these prefixes, the ASs cannot establish secure routes to the DNS servers. This is kind of dependency between routing and the DNS. So to address this challenge, so in our design, we use in-band certificate distribution, where when an address prefix owner, like an AS, originate its address prefix announcement, it will attach the full chain of certificates that certify its prefix ownership in its BGP announcements. So this can be done by using a BGP opaque and optional attribute, like legacy ASs that do not support our design will pass this attribute to their neighbors without interpreting them. So with this design, whenever an AS receives IP prefix announcements, it will have the sufficient certificates to validate its ownerships without querying DNS servers. So that solves our dependency problem. So we can show that with this design, using in-band distribution, whenever an AS receives the BGP update, it will be able to have the sufficient chain of certificate to validate the prefix owners, verify the prefix ownership. So this can be done by induction because it's true during the first hop of this prefix distribution and holds at each step. So this is a nice feature, makes the IP prefix ownership verifiable at each AS in the routing system. So any questions so far? All right. So far we have described this basic bootstrapping layer design, combining DNSSEC with in-band distribution to make both the prefix ownership secure and verifiable. And this design also faces a number of practical design challenges. The first one is that it introduces some overhead for carrying those chains of certificates. So to address, I wouldn't be able to have time to describe in detail how we address those prefix, but briefly, to reduce overhead, we have designed a certificate distribution protocol such that an AS will only send the certificates it has not signed to the neighbors in its BGP messages. That kind of significantly reduce the amount of certificates need to sign to the neighbors in the routing system. And also, for full functioning PKI, need to support functions such as certificate revocation. How can we do that? In our design, we use kind of three mechanisms together to support certificate revocation when using the expiration time included in the DNS record. And also, if they want to, AS want to revoke allocation before it expires, it can immediately announce it into the routing system. The newer issued certificate automatically revoke the old ones. And also, for some certificates that is revoked, some IP prefix that's revoked but not subsequently allocated to other ASs, we use explicit DNS revocation list to revoke those prefix allocation. Also, for improved security, we also want to introduce better key management schemes, just because the routing keys, they have to be kept online to send routing messages, which makes them less secure than those secure private keys stored offline. So there, we're introducing periodic key rollover mechanisms, makes those ASs can frequently change keys with low overhead. And also, we separate the identity keys of each AS from their routing keys, so that their identity keys can be kept offline and last for a long time. So, okay, so by using DNSSEC and inbound certificate distribution here, totally, together, we are able to make each AS obtains authentic prefix key bindings, and this basic primitive enables a bunch of other nice features, including accountable routing and accountable forwarding. And so next, I'm going to describe the security modules that we can build using this authentic prefix to key bindings. Okay, so for accountable routing, so this part design is pretty straightforward. We can also, so when AS announces IP prefix, just because, remember, because each of the prefix announcement now has a sequence of certificate chain attached to it, it can just use its key to sign its prefix announcement, attach a signature to this announcement. And other ASs, when they receive these announcements with the certificate chain attached to it, they are able to validate this AS signature, therefore certify the ownership of this AS and prevent IP prefix hijacking attacks. And similarly, when this announcement is propagated from one AS to the other AS, and following the BGP protocol, this AS will, this transit AS will prepend its AS identifier in the routing announcement to prevent past forgery attacks. This AS can use its public key, use its private key to sign these routing messages, and because the hash of its public key is this AS identifier, other ASs can validate this AS signature, and no other ASs can spoof this signature as they do not know the private key. So by using this mechanism, we are able to prevent this path forgery attack on the routing plane. So therefore, using these certificates and combined with the self-certifying AS identifiers, we are able to both doing both RH authentication and AS path authentication. So for countable forwarding, the design is slightly more complicated. So there, in order to achieve scalability, our design is to basically doing AS level accountable routing. That is, we want to hold each AS responsible for its traffic. So in the middle of the network, traffic is identified by their source AS. And if necessary, say when the network is flooded, we may separate different AS traffic in different queues or different rate limiters, enforcing AS level rate fate sharing. So this design is to incentivize each source AS to try to please the malicious senders inside its network. For instance, to incentivize them, using internal some anti-spoofing mechanism inside their network, or using some relimiting mechanism to slow down the malicious senders in their network. So basically, doing this AS level is to achieve scalability. Otherwise, we may have to keep per slow state in the middle of the network. So our accountable forwarding mechanism actually has 3 parts. The first part is a packet authentication module, where the packet carries authentication tokens that proves cryptographically where the packet, which AS the packet comes from. And this module also enables us to do path cheating detection, where we can, like the ASs can detect if whether the forwarding path is consistent with the path advertised in the routing system. Finally, using this unspoofable packet source addresses, we are able to build comprehensive and scalable and robust DOS defense systems such that we can suppress attack traffic close to its source. Okay, so let's just, it's worth mentioning that all our changes are added to a shame layer in order to be deployable. So let's look at the first design module, the packet source authentication module. So to design source authentication, a straightforward design would be making the source AS signs each packet, as in the routing system, when it announces IP prefix announcement, it signs the routing messages. But this design on the forwarding plane, unfortunately, it doesn't work very well because it introduces like non-trivial overhead. The signature is pretty long, and also signing public signature computation is also very expensive. So our solution is a system called Passport, where we use symmetric key encryption cryptography to reduce the forwarding plane overhead. So in the Passport design, each packet, it will carry a sequence of authenticators. These authenticators are inserted by the border routers of the source AS when the packet leaves their domain. So it consists of a sequence of message authentication code, each for one AS on the path to the destination. So for instance, in this example, the first MAC is computed using a pair of secret keys shared between AS1 and AS2. And then the second MAC is computed using a shared key between AS1 and the destination is AS3. So when this packet enters this network, when it crosses a domain boundary, like in this case, before it enters the AS2, this AS will use the key shared with the source AS, validate this MAC. And if this MAC validates, just because these two AS share this secret key, it proves to the AS2 that this packet comes from this source AS. And packet will be forwarded to the next hop, and the MAC will also be erased to prevent offline analysis. Similarly, this AS will use the key it shared with the source AS and to validate the MAC. and this proves the origin of the packet. All right, so now you may already have this problem, okay? How do this, this question, how do each AS actually share these secret keys? So this is the key part of the design. Recall because we can secure these IP prefix ownerships, ASs can sign their routing messages. So we can use this feature like secure routing to build a secure distributed Diffie-Hellman key exchange in the routing system. So that is, each AS, they would generate, each one generate a pair of like Diffie-Hellman secret key and a public key. And so this is using a standard Diffie-Hellman construct. That's like the public key is the exponentiation of the private key. And then in each AS BGP announcement, it attaches this Diffie-Hellman public value, and these messages will be signed by the AS, so that other man in the middle cannot modify this Diffie-Hellman value. And these messages, due to the routing's property, will be propagated to all the other ASs on the internet. And when a second AS receives these routing messages, it will combine its Diffie-Hellman private value with the public value included in the routing messages, and using this standard Diffie-Hellman construct, and obtain this pair by the shared key with the source AS. So similarly, when this message like BGP announcements reaches another AS, AS3, it combines with this private value and generates a pair of shared secret keys. So as we can see here, because each AS will originate its own address prefix announcements, and the routing system will broadcast this announcement to all the other ASs. In the end, this distributed Diffie-Hellman exchange ensures that each pair of ASs would share a secret key. So this is how we obtain this secret key and use this secret key to prove the origin of each packet AS. So now let's see, because we have this secret key, and each packet carries a sequence of MAC, we can readily use this packet passport system to detect the path cheating attack. So this attack may happen when an AS it announces some path that is legit or desirable to a source AS. But when the source AS using the BGP routing protocol choose this path to forward its packets, but some malicious AS may change the actual forwarding path. And passport system can be used to detect this type of attack, because the source AS, when it forwards the packet, it will insert the sequence of MAC according to the BGP path information. The path is learned from the BGP, and the path it chooses based on the BGP routing information. So in this case, the MAC contains the ASI, but actually the packet will be forwarded to ASJ. So there we will detect a mismatch of the MAC. So in the passport design, the destination address does not contain this intermediate MAC information. So the destination AS can unambiguously determine whether the source AS inserted the wrong MAC for the destination, or the path has changed. So if any of those MAC is inconsistent, then but destination MAC matches, it means the packet traversed by a different path the source AS actually desired to use. So in this case, the destination AS can choose to notify the source AS, say, hey, the packet are forwarded along a different path. And if this happens consistently, the source AS may decide to switch to a different path. So there, we also have a few design modules to help users select choose different paths, including some solutions like Nero, my previous work, where routers, ASs can switch paths to switch different paths, or using routing deflections, where we use the deflection rules at different routers to help ASs to switch to a different path and bypass a particular bad AS. Okay, so this is about the path cheating detection module. All right. So finally, let's talk about, after we build this authentication framework, secure routing framework, how can we use this to actually prevent or limit denial of service attacks? So there, we want to build a very comprehensive denial of service attacks to combat a wide range of them. So particularly, we are interested in two types of denial of services. The first one is basically we call it denial of edge service module, where the attackers, they send the flooding traffic to an innocent victim. So basically want to knock off this victim congested network. So the other type of attacks, we call it the denial of network service attacks, where the attackers can actually collude with each other to congest a link in the middle of the network. Basically congest a link and just next to a link. The target is not a particular destination, but a link in the network, such that all other legitimate communication using this link would be disrupted. So there, we have a number of modules to prevent this type of attack. Today, I'm going to discuss this latest work, which is published in our second paper, NetFence. So there, for NetFence, the particular design goal is that we wanted to build an inside-out defense module, where we put the network in charge of its own resource allocation to combat the denial of network service attacks. And in the same time, we also give end systems control over what they receive in order to combat this denial of edge service attacks. So the key ideas behind this NetFence design is that we place a hierarchical and a secure congestion policing loop inside this network and uses this to control the network resource allocation. And then we also couple the use of network capabilities to limit the denial of edge service attack. In the end, we want to achieve a design that is scalable and robust and also preserve the open communication nature of the network. So let's just look at some high-level ideas of the NetFence design. So first of all, we use hierarchical congestion policing to limit the damage of malicious traffic. So basically, we put per sender and bottleneck flow control state at the edge router, right? Not in the middle of them. No flow state in the core routers. This is aggregate flow state, like per sender and the bottleneck. And in the middle of the network, we do AS level policing. This is can be either done by file queuing or relimiting, like traffic from different ASs. Because we have authenticated packet source addresses, we can put them into different queues when attack occurs. Okay, so the second part is like we want to secure implement a secure congestion policing framework such that the malicious routers or hosts, they cannot evade this congestion policing action, and also they cannot fake congestion policing feedback. So to do so, we again using symmetric key cryptography. So here, packets carries their passport header, which shows which AS it comes from. And when they reach a congested link, say suppose this link is under attack. So the AS there will insert a congestion policing signal into this packet header and secure this signal, basically compute the MAC, using the key, the secret key it shares with the source AS. So this, with this key, no downstream ASs or the nodes or the hosts can modify this congestion feedback. So once this congestion feedback is returned to the source AS, the source AS can use this congestion policing feedback. If it's increase, it can increase the sender's rate limit. If it decrease, it will slow down a sender. So basically, using this unspoofable secure feedback, implement congestion policing to limit a malicious sender's sending rate. And lastly, because this congestion policing feedback is produced using the secrets shared between AS on the path and the source AS, no hosts can spoof this feedback. Therefore, this feedback can be used as a network capability for a receiver to authorize the sender's traffic. So when a receiver receives this packet, if it desires to receive from this sender, it will return this congestion policing feedback as authorization token, saying, hey, I'd like to receive from you. Otherwise, this packet will not be returned to the sender. This will, the sender will not have a valid congestion policing feedback. As a result, not a valid network capabilities to send the traffic to the receiver. This can be used to suppress the bulk of unwanted traffic. So those are the high-level design ideas of NetFence. So let's see, how it limits DOS attacks. So first of all, the congestion policing feedback, they are used as network capabilities, so that the bulk of unwanted traffic can be suppressed. Like if the receiver is an innocent victim, it doesn't want to receive from the sender, the traffic can be suppressed. It wouldn't receive the valid capabilities. And second, because we use secret keys to secure the congestion policing feedback, so those feedback will reflect the true congestion conditions of the network. And as a edge router, the source router, it will use this feedback to limit the source traffic. So our design uses AMD, like additive increase and multiple multiplicative decrease algorithm. This can be proved that each sender's sending rate will be converged to fairness. So this way, even in the worst case, we have a sender and a receiver collude to flood the network. We can guarantee that the attackers can gain no more share than the bandwidth than legitimate users. So that's how NetFence works. So through our experiments and analysis, we can actually show that in terms of limiting enough edge service attacks, our design NetFence performs similarly to a capability-based DOS defense system. And in terms of limiting enough network service attacks, it can provably give each sender its fair share of bandwidth. This changes enough service attacks actually to predictable delay of services. So basically, we are able to prove this following theorem. If we have G good users and B bad senders sharing a bottleneck of capacity C, and regardless of how attackers behave, each good user is guaranteed a fair share of its bandwidth. So basically, this is modified by a parameter that shows how effectively a sender transport protocol can use the available bandwidth allocated to it, and the parameter modified by determined by the design of the close to one, determined by the implementation of NetFence. So so this ideally we would want this form like B to be 0, right? We would want the bandwidth to be fairly shared among good users, but that would require that the network we would have some mechanism to be able to distinguish good traffic from bad traffic. But in our design, we do not make those assumptions. Although if we have this capability, our system will perform better. Yeah, that's a good question. I didn't actually talk about the detail. So this rate limiter, what I was doing is actually per sender per bottleneck. Yeah, it's aggregate per flow. Like if I do per sender and per destination, right? The sender can actually diffuse its traffic to multiple destinations, get unfair bandwidth share. So I'm actually doing per sender per bottleneck ID, to bottleneck in the middle of the network. The congestion policing feedback here, inserted is actually has the identifier of the congested link in the network. Yeah, that's a good question. I just don't have time to cover those details. Yeah. Sorry. Okay. So now let me just briefly describe how we actually evaluate our design. So again there's many aspects to evaluate. first of all, we just want to know, does it work? Okay, this is a pretty comprehensive architecture. And also, how well does it perform? There's like overhead, we introduced on DNS, and also on routing, and also like in the forwarding plane, we introduced this defense modules. And also the question about adaptability. Our goal is to make our changes adaptable. So first of all, we want to answer the question whether the changes gradually deployable or not. And second of all, we want to say, okay, whether they incentivize early deployment, whether early adopters gain immediate benefits, or they have to wait until everyone deploys those changes to gain security benefits. So again, I don't have time to talk about all those aspects of evaluation, particularly for overhead on DNS and the forwarding. Our experiment shows that those are low, right? You can see them from my papers, and I'm just going to talk about the overhead for inbound distribution. Okay, so does it work? We actually just built this system using routers like click router and ZOP. This is like a routing module, and like forwarding plane, we have like net FPGA evaluation, and we ran some small scale testbed environment. Just we couldn't run it like the internet. So basically, we built this network, we bootstrap it, we observed all those successful bootstraps and launcher attacks. So those are kind of described by some of our papers. So this part, we have a proof concept evaluation, our conclusion is like, it works. So the other part is like, how we evaluate this BGP overhead. We use BGP for non-trivial stuff, for actually as a certificate distribution system. So how much overhead does we introduce? So for this part, we did like trace-driven emulation. So what we did is that we obtain realistic BGP update traces from those BGP root view routers, and convert them into the particular traces, like in our format, like the IPA traces that carries those certificates. And then we feed those updates, the real-time update, to our routing daemon that process those certificates. And then we measure the BGP overhead. Okay, so here this slide shows the BGP data we collected. So it's almost a month, like 27 days, and among those traces, we observe more than like 35K ASs, and this is like more than 300K prefixes. The particular vantage point is the root view server. It has like 37 peers, like different ISP peers. This is like almost like similar to like a large ISP's router, and total update is like more than like 100 million, and on average it's like 44 updates per second. So first, from this data, the first thing we get is to infer this delegation hierarchy, because for each of our BGP update, we need to carry the full chain of certificates. So this figure shows the distribution of delegation hierarchy in the IP prefix delegation. So here, we show that like most of this delegation is actually very shallow. Just means that the certificate chain is, in practice, is actually short. We wouldn't see a very long certificates. So here in this graph, the x-axis is the time, and the y-axis is the average total, aggregate average like update traffic, from all the peers we receive BGP updates. So the blue line here is the vanilla BGP. So this is like the BGP feed, what it's like, and the red line here is the our IPA traces. Say what if the internet using BGP to deploy the certificates, what is the overhead? So here we are trying to do upper bound estimate. So what determines this overhead is actually the frequency for key rollover events. Like we have this key rollover mechanism for better security. There, we actually assume a very frequent key rollover events. Like every AS, they do weekly routing key rollover, and they do monthly identity key rollovers. Like in practice, we assume this should be upper limit. They shouldn't change their keys so frequently. And also, whenever they change keys, we actually inject new updates, carry the new certificates into the BGP system. So here, as we can see, it does, our design does increase the BGP update. So normally the BGP update is like below 10 kilobit per second, and ours now is like below 100 kilobit per second. But recall this is like a large, simulate a large ISP with like 37 peers. And most of the car routers will have like 10 gigabit per second bandwidth. So we consider this overhead is acceptable. And also this graph, the x-axis shows the update message size, and the y-axis is the cumulative distribution among the BGP messages. Again, the red line is our design, the blue line is vanilla BGP. So here we can see that a lot of overhead comes from the increased packet size. Because the certificate each one is around like 700 bytes, so the BGP message size has increased compared to vanilla BGP. And then in our design, because we use BGP to do the certificate distribution, each router would need to validate the certificates, and after they validate it, they propagate to the next hop, right? So it also introduces some processing overhead to validate the certificates. So this graph on the x-axis shows the day of the traces we collected. The y-axis shows the cumulative, the total CPU time we spent on processing the BGP updates. So again, the blue line is vanilla BGP, the red line is our design. So as we can show, again, we increases the BGP processing overhead a bit, but this overhead is acceptable. The router does not spend all day, like 24 hours doing it. It spends about like 15%, 10%, 1.5 hour over 20 amount of time doing this update rather than all the CPU time. And also, another question we want to look into is that whether we can, the routers, if we have a burst come in the update traffic, whether a router can keep up with processing those certificates, or it will build up a queue, exhaust its buffer. So there, we fit our traces. This is actually, when we choose a random day traces to our IPA router, and this is the implement using a typical PC, and then the x-axis is like the arrival time. The y-axis is the time after our processing. And again, we compare with our processing time and arrival rate. So if we see a gap there, which just means we lag behind. But here, we see these two lines actually overlapping, which means a single PC can catch up the processing of realistic BGP traces. All right. So another question we are interested in whether the designs we introduce are deployable or not. And here, in order to answer this question, we actually ran an experiment on the real internet. What we did is that we modified a BGP Quagga, router open source BGP implementation, and take a new configuration command like trans attribute, and then we add a configuration command to a router's like configuration map file to like route map to add these attributes, and then we asked the rep RS team use their BGP beacon framework to inject this attribute into the real internet. So this graph shows the test result. The x-axis is the looking glass, like the vantage point. We collect the BGP updates. And the y-axis is the number of updates actually, from our vantage point. We see that carries the particular test attributes. So the red line is like all the updates, and the blue line is attributes that the update carries our attribute. This is, as we can see, we receive like a fraction of updates carry our attribute, but like a lot of them are kind of lost. So this, we suspect, is due to a bug. This is actually the test. In the newspaper, you may read, some Duke researchers broke 1% of the internet. So that's the one. So we actually think, it's actually a very prevalent router, vendor. Their bug stopped all our updates. But it's, again, still we see, a non-trivial fraction of updates reach our vantage point.
Most people drop attributes when they cross PS boundaries because they don't want the information. They don't want someone else to rewrite the traffic.
Okay, you think that's that's actually not BGP spec. It's not. Yeah. Yeah, it's not compliant with the. I mean, if they're compliant with the protocol, which they should, as a vendor, carrier grade vendor, then yeah. But I think the presentation, it's like they actually reset because of the bug. They reset it. So we expect to run this again, later, after half a year or something, and to see how it works. But I think the initial results we conclude is pretty promising. So here it shows actually how our test results propagate, like the AES path length in the updates we actually get. We see like here, there's like most of them is longer than 2, meaning that they actually pass legacy ASs. The longest one observed has like 10 AS path lengths. And here we do not count any AS padding, so they are distinct ASs that do let those paths, the attribute paths. Okay, so just quickly go through. So here, we also analyze the adopter, whether we prevent incentives for early adopters. There, we use the adaptability model we use to analyze this packet source authentication system. Basically, it's just hard to see whether we are adoptable or not. And just to do so, we actually compare it with another design like secure BGP. Basically, try to see whether we actually lower the deployment hurdle, provide higher incentives than previous work. And so basically, the model, we model incentive as the security benefit minus the cost for deploying this particular system. So in our design, because it does not require a registry to set up a different, PKI to deploy it, and the security benefit that we obtain is similar to a PKI, like ISBGP's proposal. Therefore, the conclusion is that, the incentive for registry is higher than secure BGP. And also basically, AS deployment will depends on the internet registry deployment, because without their certification, the AS prefix ownership cannot be validated by other ASs. So since we have a higher incentive for registry, there's a higher likelihood that the registry will deploy our system than ISBGP. Then in this case, the ASs would have more incentive to deploy. So our analysis shows that actually, if the registry is deployed, 78% of ASs can immediately obtain their prefix ownership from the registries, just because the allocation is typically very shallow, just like from registry to one AS for 78% of ASs, and they can use those prefix ownership certificates to prevent hijacking attacks. And we have also detailed analysis in our work, but just briefly. So here, one problem, security problem, this design may face is this self-certifying AS identifiers. For something like self-certifying, usually, entity can just whitewash their tarnished identities. But in our design, we can actually prevent this type of attack, because the ASN, a valid AS identifier, they must be bound to a valid IP prefix. And this part is actually certified by external trust, so they cannot whitewash it. And they can probably mint a lot of child ASNs, but this causes little harm. This basically just make their AS path longer and less preferable. So basically, we are not vulnerable to those attacks. So in summary, right, it's like a very dense talk. So in this talk, I basically described a route, like an internet architecture, IPA, which is a dirty-slate design that introduce accountability to the internet. We use lightweight and adaptive changes, like we use DNS to create IP prefix ownership certificates, and we use inbound distribution to bootstrap accountability internet. And with this mechanism, network identifiers are verifiable. And use that, we build some, we do the accountable routing and forwarding modules, and to secure the internet against various attacks. So that's about this talk. So when looking, put this work into the bigger picture of my research agenda. So basically, most of my work in the past have focused on designing the future internet architecture with both, under both technical and social economic constraints. So this work is basically about considering this achieving the security of the network. And also, I have another like branch of work, how to build like better, more scalable and more fault tolerant internet routing architectures. And I also, like this Nero is kind of my thesis work, but the rest of it is my work in the past several years. And also, network economics, where we consider issues like how to address using technical approach to address network neutrality issues, and how to provide robust incentives to participants to abide on network protocols. So looking forward, I hope these like different pieces will come up together, become like a coherent future internet architecture. And I'm actually part of a future internet architecture team and working on building a better internet for tomorrow. All right, so finally, most of the work, is done jointly with my students and postdocs. They did all the heavy lifting, and some of them is done with my collaborators. All right, thank you. Yeah. Do you mean the?
The passport seemed like combined two things. One, I had my own key, and then I secured my key with the series of AS that I expected the packet to go through.
No, you share petabytes keys with every AS on your path.
So I, as a sender, am more or less telling the transit provider what I expect them to send the packet through. And if they don't send it that way, then security doesn't work.
So it's actually passport does two things, right? It's like one thing is like for the intermediate one to validate whether you are come from where you claim you are from or not, right? That's the authentication part.
So does that part needed to follow the AS path?
That's right. Yeah, that's need to. And if you actually, and then the second part, if you don't follow the path, the MAC wouldn't match. Therefore, we also detect the path cheating attack.
It just seems that I, as a transit provider, don't want one of my customers telling me where to send the packet.
No, it's not your customer telling me. It's the path. Actually, the path, the MAC you put into is based on the BGP announcements you.
BGP announcements are there that not so you're creating this passport that sets the AS path. You're telling me what I'm supposed to be doing as the transit provider, and it seems there's a possible problem with that part of the.
Let's see. Actually, it's not telling you what you should do. You don't have to, right? But if you advertise, say I'm going to send it through this provider, but you're not going to do that, right? I mean,
well, that's what the AS path tells you. The AS path doesn't tell you. It doesn't. When I send you the AS path, I'm just telling you what's in there right now. I don't even know what's actually there. I'm not validating in any sense, right? Are you assuming that the AS path is validated as well?
No, the AS path should be authenticated in the BGP routing. So if someone forge the AS path, that's a path forgery attack, because the AS path is actually can be used as a path selection parameter. If I have policy routing, say this is a packet go to Iranian network, I totally don't want it. But if you fake it, saying okay, I didn't want to send your packet through Iranian network, but I actually did. I would consider this as an attack. I mean, I'm not telling you what you should do, right? But if I detect this, I would switch to a different path that I prefer to use based on my routing policy.